This conference will now be recorded.
Okay, we'll make a start. Good afternoon, everybody. I think myself and Mark, we did this presentation just over a year ago. It's actually probably only a week or two before we all went into lockdown, so it'd be slightly different this time. We're doing it remotely, but it's still a really good and interesting job to talk about. And it's relating the refurbishment works we did in 2017 and 2018 with a look to some of the future ongoing maintenance to this historic and really important structure. And Mark, do you want to take us on to the next page? Yeah, so I'll basically do the first bit, and then Mark will sort of take over in the middle to talk about the refurbishment works, and then what we'll do is we'll have a bit of discussion on the future bearing replacement, which is it's still very much in the pipeline, but it's probably in control period 7 now, so it's a few years away before that'll be looked at. So we'll start off with a look at the structure and the history of it. So if you could just try and keep pace with me, Mark. Yeah, just a bit of a note about the speakers. Myself, I'm the rail engineering manager for Buckingham Group. We do a lot of work on heavy rail and light rail, and my area is sort of in the north of England. I've acted as a CRE and SEM on a range of projects across the north. My background is mostly bridges, but I do a lot of multidisciplinary projects as well, and I currently do a lot of ECI. Mark, who, if you want to talk about yourself, but Mark was actually seconded to our team and was actually on site for the refurbishment works, and I think obviously got quite a lot out of it. Okay, Runcorn Rail Bridge basically carries the electrified twin-track Liverpool West Coast Main Line between Runcorn and Widnes, so obviously quite a strategic and important structure. Crosses the Mersey at a pinch point, which is obviously the shortest distance, so from a bridge perspective that makes sense. What we found during our works is that makes that quite a challenging environment to work within. So if you imagine at the pinch point, the river actually, the flows and the tidal range actually increase. It's part of a much longer viaduct, and I'm sure if you're familiar with it, you know there's a series of arches both to the south and the north that take the track on and off it. It's grade 2 listed, so everything we did we had to seek listed building consent for. And just a bit of history: designed by William Baker and opened in 1868. So it's quite an elderly structure, but still in good condition. So just looking at how we sort of approach the bridge, we've got our main compound was on the Widnes side. That's where there was more space, and you've got the north abutment, north pier. Each spans about 96 meters, I think, so it's fairly sizable, and it spans over the ship canal, which gave us a few operational issues, which Mark will talk about in due course. It's a three-span wrought iron lattice truss through bridge, 93 meters the spans, with 23 meters clearance over the shipping on the Mersey and the ship canal. It's not just the ship canal where we have river, where we have traffic. We also encountered a few issues with the local yachting club after I think they'd have some difficulties and potentially not been given the full truth about the Mersey crossing project and had their activities severely curtailed. So each span, 2 lattice trusses formed from twin box sections, wrought iron lattice work, deck formed from wrought iron plates with cross girders and rail bearers, and sandstone piers and abutments with voids. So this is founded on solid sandstone in the river. I think each pier is, the outside is quite hard, that's gritstone, but inside's all the sandstone. Next slide, please. Just there's an old picture. It's very ornate, the bridge. We've done quite a bit of work to try and preserve that. So could Construction commenced 1863 and opened to traffic in 1868, so 5 years, which is actually not a bad feat considering what they had, the challenges that they overcome in that environment. It's the first bridge crossing the Mersey estuary, and there was originally a walkway which was open as a public alternative to the ferry. It's still there, and it provided us with some really good access onto the structure, but you can't get onto the south shore. The steps have actually been taken away, and it's closed to the public in the 1960s when the adjacent Silver Jubilee Bridge opened. Next one, please, Mark. Just to give you, that just gives you an idea of how they constructed the bridge. I think that's pretty impressive. When we've been to the site and we've seen the tidal flows, it's pretty. It can be a pretty frightening environment. So to do it with the technology there at the time was really impressive. Next one. Another one of the construction, and you can just see those 93-metre spans going up. And the next one, Mark. So in terms of our project, what were we doing? We were contracted to look at refurbishment of the bridge, and ultimately this was all geared around replacing the bearings, which have never really functioned properly on this structure. So phase 1, 2015-16, a lot of visual intrusive surveys. So things like coring the piers to prove that they were solid and that they weren't voided. We do know that the abutments are voided with sort of arches inside. Structural assessment, so Arcadis were finalising a finite element analysis of the structure to actually assess the structure, and that model's really important because when we're looking at things like in phase 3, the bearing replacement works, that's really critical because we need to understand how that structure behaves when we try and actually apply outside loads to jack it up, and a 3D survey using a combination of ground measurements and drone. Phase 2 in 2017-2018, east walkway refurbishment, stone turret waterproofing, and the pier fender refurbishment. Mark's going to talk in more detail about that. And then phase 3 is the bearing replacements. My gut feel is that it will be later than 2024. I believe that's probably towards a few years later than that. It's in control period 7. Next slide, please, Mark. So we'll talk about phase 1. The bridge was inspected by rope access and 3D surveys using a combination of drone measurements. So those sort of drone measurements, they're still a little bit crude, but the technology is really coming on, and what it allowed us to do is fill in the gaps in the model to some of the really difficult areas that we couldn't get to. Intrusive works, the piers, that's basically coring them, and that's how we know that it's sandstone inside and it's gritstone on the outside, and a structural assessment using a 3-dimensional finite element model. As part of that, we also did some initial feasibility work on the bearing replacement. It's quite a difficult structure. The bearings are sort of tucked away. On a modern bridge, you'll get a bearing shelf or your jacking shelf, so you can actually get in and actually push the bridge up to get to them. The construction of this bridge isn't terribly helpful. You've got these reinforced diaphragms around the piers, which take a lot of the shear forces. When you go away from the pier, you're into the open lattice work, which basically means you've got no, even if you could create a bearing shelf on the outside of those piers, you can't really jack there without some significant strengthening and temporary works. Otherwise, you'll just shear through all the lattice work. So what we did identify as part of these works is urgent maintenance to the east walkway. It's cast iron. A lot of the piers were cracked, and there were sections that were sort of held together by temporary scaffolding. So it was a risk not just to rail workers and maintenance workers, but also to the navigable traffic below. The other thing we identified, there was a historic navigation bell, which was at risk of being lost. Next slide, please, Mark. Just an image there of the 3D survey model. It's a really powerful tool, actually, not just for developing the model, but for planning construction works, for discussions with stakeholders. And the next one. Do you want to take over from here, Mark?
Yeah, as I was going to say, Richard's probably a good point for me to take over. So, good afternoon, everyone. So, I'm Mark Fletcher. I work with Richard on the Runcorn Railway Bridge refurbishment as the sort of the lead construction engineer. So, in terms, as Richard's already said, there's quite a few elements to this project. Our main aim was to sort of deal with some very sort of time critical issues related to the condition of particularly the Eastern Walkway, and also just general sort of refurbishment and maintenance activities that were deemed to be sort of necessary at this point in time to keep the structure in operational until the more sort of more comprehensive repairs that will be associated with the bearing works, which will be, as Richard said, probably sometime in the 5-10 years distant future. So I said this project was now mainly focused around trying to keep the structure operational because it's such a key strategic asset on the West Coast Main Line to Liverpool. So in terms of the work we did, it was to replace or refurbish the cast iron walkway parapets, which I'll come into in a few minutes. And I'll go into detail on quite a few of these in a few minutes. Also to repair the actual walkway itself, including the cantilevers which hang off the side of the structure. We also took the opportunity to do quite a lot of waterproofing to try and resolve some of the issues with water ponding and water getting into sort of enclosed space, including the boxes in the lattices and also on the stone turrets at each end of the structure. We also had to look at how to save the navigation bell, which is, I'll come on to a bit, it's quite a difficult area to get to. It's very remote, very difficult to access. And as a result, it had been the support structure had started to corrode and was starting to fail. So it's very urgent that something was done there. And the final part was to look at the timber fenders, as this structure is still part of a navigable waterway. It's essential that the actual structure is protected. Not so much from ship impacts, but often particularly in the Mersey estuary itself, because of the high flows, any debris that's in the river will get thrown against the piers. So these fenders provide some level of protection to the stonework. So to give an idea of our team, Bookings were the principal contractor on site. We had two clients, predominantly it was Network Rail for the structure itself. But we also had a second client in this case, which was a company called Innovin, who operate one of the chemical works in Runcorn. They have a power supply cable that runs across the structure, and that also needed some maintenance, which then they took the opportunity to do that whilst we were there and asked us to do the work for them. And then you've also got, and I'll come on to this again, there's the NR air operations, which is actually normally air operations associated with sort of inspection of the track, but in this case they actually helped us with the navigation bell. In terms of the other sort of key players in the refurbishment works, we had Tasika Industrial, who were kind of our sort of principal subcontractor. They were responsible for all the steelwork and painting activities. As Richard said before, Arcadis were our sort of lead designer. They were responsible for both the refurbishment works and all the works associated with the bearing assessments. And then we also had a couple of specialist marine contractors. Bookings normally focus on rail projects, so we sort of had to bring in those specialists to support us with the water aspects on this particularly challenging site. So we had Carmet Marine, which is a local company based in the Wirral, who helped us with the actual fender refurbishment, and a company called Safety Training International, who provided us with marine safety boats and also safety advice. So one of the challenges of this particular project was the number of interfaces. So we had, obviously being over water, we had quite a few interfaces with various organisations, including the MMO, the Marine Management Organisation. Had to secure consent from them for working in the river environment. We had to get permission off the Coast Guard to operate in the river. Again, with it being a navigable channel, it requires their permit. They have to be aware of who's operating that area. We were working over the Manchester Ship Canal, so we had to also seek permission and consent off Peel Holdings, who now own the ship canal itself. That had a few restrictions on what work we could do. Particularly, we couldn't do hot works, so cutting and grinding when there was ships passing underneath for obviously obvious reasons. The Crown Estate, obviously, this was a maritime environment, so the Crown Estate actually owns the land in the middle of the estuary. So again, we had to seek consent there. Holme Borough Council with the planning authority, so all the listed building consents and the permissions to use the land each side of the structure. Again, we had to seek permission there. When we dealt with the navigation bell, we had to use a helicopter, and I'll describe this in a bit more detail later in the presentation, but obviously that then requires us to work with air traffic control and with the airport, with it being just a few miles down the estuary. We also weren't working alone around this structure, so we also had to interface with other Network Rail projects. So there was a resignaling project underway at the same time, run by Network Rail, and also Buckingham's as well, which was resignaling the Weaver to Wavertree route. We also had to work with colleagues who were working on the adjacent Silver Jubilee Bridge. So whilst we were on site, the new Mersey Gateway Bridge opened, and at the same time the old bridge was closed for a major refurbishment, and they were working sort of side by side with us doing, well, as it turned out, very similar work, but it did mean that we had to share resources. We also had to work together, particularly in terms of marine safety. We also had an interface, as I said, with Innovin and their cable route. That cable route was a particularly vital power supply, and there's essentially it's a critical backup, and if it was taken offline, it would have quite some serious costs associated with it. And obviously, we were working in the two site compounds in residential areas. In particular, our main compound was in a very, very residential area and backed onto a school, so we had to be very careful there as to not cause too much disturbance to local residents. So coming on to site constraints, so it was a particularly challenging site to access. The bridge itself is around about 40 metres above ground level or above river level. We've obviously got the adjacent Silver Jubilee works, and they were, like I say, they were doing similar works to ourselves, so we had to make sure that their when they were scaffolding, that we weren't passing underneath their works to get to access to ours. So that was quite a complex, challenging interface at times. We had to stand down when the ships were passing under the ship canal, so we had to monitor the shipping each day. So each morning we'd have to contact the port authority to get a list of the ships that were planned to come through and get a warning before they approach the structure. The Mersey estuary itself, at this particular location, because it's a pinch point in the estuary, there is a very high flow rate through this area. So it was one of those situations where if you did fall in the river during that period, you would be carried several miles before you could be rescued. So it was a very, very fast flow, and a lot of the time at the very highest spring tides, we had to actually stand down during the peak flows because it would be too dangerous to even launch the safety boat. And then when the tide's out, we've then got the opposite problem, which is we then got dangerous mud flats with quicksand and other potential risks. So it was a very limited access, very challenging place to work. We also had to consider the fact that we were working next to a live railway, with it being the West Coast Main Line and also quite a key freight route. There was very limited access to the track bed, which left us with a very narrow 2 metre wide pedestrian walkway on one side of the structure for the majority of the work, aside from a few weekend possessions and blockades. The compounds themselves were in residential areas, quite narrow streets, so it meant delivering materials was actually quite difficult and had to be planned around peak times, particularly if we were adjacent to a school, so we had to avoid certain times of day there. And as I said previously, the Innovin cable itself, it runs alongside the walkway. We were doing a lot of intrusive works, blasting and grinding, cutting, and the risk of potentially severing that cable would be quite significant. So we had to be very cautious as to how we address that. So because of all these constraints, there was quite a lot of CDM and safety to consider on this project. So because of the work we were doing, there were actually quite a few. We had 4 of the sort of key Schedule 3 risks from CDM 2015. So we had lead exposure from the paint, which we were removing from the east walkway. We had to work, obviously, we were working over water, in particular the fast tidal flows from the Mersey. We had two separate sets of electrification to deal with, the 11 kV Innovin cable and also the overhead electrification on the railway as well. And we had to deal with some very, very heavy cast iron components. So some of the heaviest components which I'll come on to in a moment, were up to 450 kilos each. And because of the very, very tight site, we had to use a lot of manual work. It's a very, very manual process. There were very limited opportunities for mechanical lifting equipment. And so all the operations had to be very carefully planned and coordinated to achieve them safely. And then in addition to that, obviously, with us being adjacent to the Balvac site, and they were also having similar issues with lead exposure, because they were also blasting and painting. So there was that coordination. And also in terms of their scaffolding exercises, there was the risk of objects falling from height. So again, we had to ensure that we weren't passing underneath or working too close to their sites when they were doing that. So temporary works was probably the most significant cost element on this project. So in this case, the permanent works are actually, if this had been on a normal bridge, it would have been relatively straightforward, but just said the location meant we needed some pretty impressive temporary works, including 3 90-meter long suspended scaffolds, which were hung off the underside of the bridge and off the side of the bridge. So because of all that additional weight, there was actually a further load assessment undertaken by Arcadis in that temporary condition, with all the extra weight of the scaffolding and the encapsulation as well. So there's quite a lot of extra wind loading on that eastern walkway in particular. And just some views and a bit of a comparison really as to how things change. So on the left there is a photo taken from when the structure was originally built, and then on the right is sort of the modern equivalent with hopefully it's very, you can see the similar principles, but I think we've moved on a little bit, and I think and try to make things just a little bit safer for the workforce. And so in addition to having the suspended scaffolds over the river, we also had 2 20-meter high scaffold towers, one at each end of the structure to give us access. So each of these structures had two purposes. One was to provide pedestrian access, so there was staircases, but we also had to have what we called loading bays with winches to effectively haul all the materials and equipment from ground level up onto the bridge. In addition to these, we also had some scaffold jetties in the river itself, which provided us with access for the safety boats, and also when we were doing the turret works to allow us to get access to the working platforms during high tide. And we also had some turret access scaffolds to get up onto the very high stone parapets at each end of the structure. Just want to quickly touch on one of the design close calls we had during the project. So whilst this is the picture you can see there on the right is the top of one of the loading bays. So the idea is we would have these 2 winches, which would be used to lift and lower materials. But during works, we found that to make that happen, people were leaning over the side, which we felt was not particularly safe. So we redesigned our scaffold to basically improve that safety. So we put on longer Nico rails. We added attachment points for harnesses and inertia reels, and we used different hoists to allow it to pass over the scaffold and remove that need for people to start leaning over. I think we're over in the end we were quite happy with the way it operated. I think it was a much better solution in the end. So coming on to the cast iron parapets, so each span is made up of about 200. Each one has about 30 bays. Each bay is made out of 6 components, so that's about 200 components per span. And all those had to be removed by hand and hauled away using trolleys on the walkway. So of those elements, the bull nose, which is the one you can actually see in the picture there, is the piece that hangs off the bottom of the walkway. It's also the heaviest component, and as you can see there, it's quite an awkward shape, not particularly stable, quite difficult to transport. All those items, every single one had to be removed from the structure, and the intention being that we would remove them and take them down to ground level and off-site for refurbishment, including grip blast and paint, and then bring them back. However, a lot of these elements were fabricated in the 1860s from relatively poor quality cast iron, so it's grey cast iron. It's fairly brittle, and over the last 150 years, the combination of the weather and the movement of the structure had led to a lot of those elements becoming fractured. There were some quite significant cracks in some of them, and in some cases, parts of the elements had already fallen into the river. So where we couldn't repair, where there were significant defects, and such as large cracks, we had no choice but to replace the defective components with modern cast iron. Now, modern materials are much better, they're much more ductile, using this what we call spheroidal graphite, which is why it's known as ductile iron. It's quite a common material. During the optioneering for this structure, other materials were considered, such as aluminium castings or even fiberglass. However, this structure is Grade 2 star listed, and it was Network Rail felt it was appropriate to maintain the existing materials and use the existing materials when we replaced, and avoid having a mixture of materials across the structure. So in terms of the parapets themselves, from a civil engineering point of view, this is quite an unusual task. We're usually dealing with concrete and steel, so cast iron was something quite new to me and quite to a lot of the team. So I'll just quickly run through the process. So the first part of the process after we've removed these elements off the structure is to then create the patterns. So a pattern is a timber replica of the original material, or the original component. You can see a couple of them there on the right hand side. You've got the first one, so on the left is what we call a bottom element, and then you've also got a bullnose element on the far right. So these patterns are not an exact replica. They're all slightly bigger than the final shape you're trying to achieve, and that's simply because of heat shrinkage. So these patterns have to be made large enough to cast it, and then allow for that 2% shrinkage as it settles into its final position. It's a very skilled task, as I said. The foundries where we got these made had to spend several weeks crafting these patterns ready to run the first test castings. So the casting itself, basically it's pouring into what we have created. The patterns are reusable, but the molds are not. So each pattern can make multiple molds, but each mold is used once. These sand molds there's two types. There's boxed and boxless. So you've got a boxed one there on screen. Boxless is a lot more expensive because of the way they have to be made, but they do take up less floor space, and I'll come on to why that's a key consideration in a minute. It's also possible to create internal voids, which again was quite important because a lot of the components we were using were hollow, using a bit of a sand core. As I said there, each individual component, so we had to fabricate around about 350 new components to go on the structure, and each one of those had to have a new mold made. So in terms of the actual casting, so the molten iron has to be very, very carefully temperature controlled. If you go too hot, you get a blowout, and then basically the mold collapses. And if it's too cold, you end up with a lot of internal voiding, which then degrades the integrity of the whole element. It has to either be melted down and recast, or we have to do a lot of work to try and repair and sort of correct some of the defects. Each of those castings has to be left in its mold while it cools to prevent it from warping. So the heaviest element was the bullnose. That's about 450 kilos, and that takes around about 36 hours to cool before it can be removed from the mold. And some of the lattice work in the parapet panels we were quite concerned initially with those because they are much more susceptible to warping. But in the end, there was actually relatively few issues with warping. It was quite successful. So once the materials, the components have been cast, they come out of the molds. They have quite a few extra pieces on there which are associated with the actual casting themselves to allow them to pour the molds. So there's then a lot of work then to convert those into something we can use to basically grind off anything that shouldn't be there, and to prepare and also put a surface finish on the elements. This is something we've actually discovered during the works, actually, how to define what that finish standard should be. So we had quite a lot of discussions between ourselves, Network Rail, and also the foundry to try and identify what a suitable standard would be. And I think we were, in the end, Network Rail were very happy with the final finish of these elements. So you can see there we had a couple of goes at the trial erections. The first one was not quite the right length. Again, this is the challenge of trying to sort of replicate something that was made 150 years ago. We were having to sort of piece it together from just the components. There were no drawings to work from, so we had to. It was a bit of a trial and error, really. So one of the key issues of the whole project was the production rate of these elements. As I said, we needed over 300 of these made, and if they require a lot of floor space, each of those molds takes up quite a large area. And despite bringing a new part of the foundry into operation to store these molds, we were still limited to around about 25 elements per week, simply because we couldn't find, there wasn't enough floor space to have to do any more. And even as I said earlier, we did consider using the boxless method to try and get us a few more, but as I said, the difference was around would have increased production right around about 3 or 4 a week. But the cost was considerably higher, so in the end we decided to stick with the boxed. And then I said the final phase really is the finishing. So after they come out of the foundry, they've been prepared to a finish, but there's still going to be minor defects such as minor blowholes that can't be corrected in the foundry. So they then get shipped to a paint workshop and for some filling and painting. And to protect this cast iron for the next 120 years, it's been given a full new paint system. And that takes roughly a week per item. So essentially what we'd do is at the end of each week, a batch would be sent out from the foundry, taken to the paint shop, taken another week in the paint shop, and then after that it would be delivered to site for installation. As I said previously, all this had to be done by hand. Each element had to be removed from the structure and then hauled back up again to reinstall it. We had a series of trolleys that ran up and down the structure we prepared some special runners, which allow us to do that safely. And it was, like I said, a very manual job, not easy. And I said the method we had to continually revise and update and reconsider our method statements and methodology to try and minimise the risk of injury. Unfortunately, due to that process, I think we avoided any real significant injuries, which was a testament really to the effort everyone put in to make sure that it was done safely. I think the key thing here was that we were never really limited by our installation rate on site. It was always the key frustration was always how fast we could churn it out in the foundry, and the foundry was always going to be the limiting factor. So it took quite a few months to actually get all these things reinstalled. And then there's just some pictures here of that reinstallation occurring. So you can see on the bottom right there, that's the final installation, and we've tried to replicate as closely as possible what was originally there. I think, as I said, Now Rail were very happy that with the final finish. I think one final complication that we hadn't really anticipated was because of the duration of the installation process. We then had an overlap. So we had originally intended to get the parapets installed and then do the works on the fenders, which have to be done in the summer because of the restrictions of the license we got with the MMO. But unfortunately, because of the long timescales and the longer timescales that we'd anticipated to fabricate the parapet units, we then had to coordinate the activities to ensure that we weren't working overhead when we were also doing the fender works. So whilst we were also there, we also had to repair the structure itself. So the bottom left image there is actually the cantilevered beams which support the eastern walkway. The end supports had largely corroded away. There wasn't an awful lot left supporting the cast iron parapets. So we took the opportunity to replace those and replicating as closely as we can to comply with the listed building consent using modern materials. And this was quite challenging as well because the structure itself has moved over the last 150 years. There was, as I said, the actual positioning of the new elements, which were all uniform, and then trying to fit those uniform components onto a non-uniform structure was quite challenging. So we had quite a lot of debate as to the best way to accommodate those tolerances. As you can see there's some slotted holes, and there was a number of different, in some cases, bespoke solutions to try and get like I said, this very regular new castings to fit onto a relatively sort of irregular structure. So one of the other big challenges on this project was also the turret waterproofing. So at each end of the viaduct, there are 2 large stone turrets. I'll show you a picture in a second. They are a further 20 metres above rail level, which makes you about 40 metres above the river. And they are inaccessible except during blockades. We have to have full isolations, and because of the timescales involved in setting up the scaffolds and getting access, it can only really be done with long weekends. Fortunately, the Weaver to Wavertree project, we're also working in this area, so we were able to sort of share work sites and share possessions to try and sort of get the best to minimise disruption to customers, and also to sort of minimise the sort of costs to both projects. And in some cases, even with scaffolds, some areas were completely inaccessible, and therefore we had to bring in experts and specialists to basically abseil down to some areas of the structure to clear out debris from drainage pipes and to remove material that had become clogged in around the bearings. So you can see here, there's some pictures of us gaining access. So you can see in the left-hand photo there is a temporary scaffold on the railway, which then allows us to climb up above the overhead wires onto the first level of the turret, which is above the railway itself, and then there's a second lift of the scaffolding, which allows us to get onto the very highest parts, which are, as I said, they're about 40 metres above the river. And it's, as I said, from personal experience, it's quite an interesting place to get to when it's quite a windy place when you're on the top of that bridge in winter. So I'm now going to come on to the navigation bell. So this was one of those sort of key parts of our listed building consent, was to preserve this bell. We had 2 options. One was to try and repair the support structure in situ and allow it to remain in place, or we had the alternative, which was to remove it and put it on public display. Having gained access to the structure during our project, it became apparent that replacing it would not be a viable option. It was a very difficult place to gain access to and get materials to, and we'd also be leaving future generations with a significant maintenance liability, which in the end we decided was unacceptable. So we then were left with the challenge of how to try and remove this bell from the structure without damaging it. Taking it through the lattice work wasn't an option, so we had to either lift it off from the river, or in the end we decided the only viable option was to actually use a helicopter to lift it off and carry it to the shore. So this was organised through Network Rail Air Operations. As I said, normally they would do track inspections, but for this particular case they used their contracts to allow us to do a lift. So obviously, operating a helicopter in close proximity to an operational railway would not be acceptable, so it can only be done during a weekend. There are also quite stringent weather restrictions, which meant we could only do it probably during the summer months, when we're more likely to get those calm conditions. We also had timing restrictions from the airport, which meant we could only do these activities at quiet periods, which were typically first thing in the morning, last thing at night, and at the weekends. So in the end, we had to try and accomplish all this in a 30-minute window on a Sunday morning, whilst we had a railway possession. We also, to protect the public and also river users, we had to ensure there was a full exclusion zone around the structure, both on the river and under the ship canal. Again, further difficulties in terms of coordination. So in all, it took us around 2 months to plan this operation, and in the end, it took the sum total of about 3 minutes to actually execute. But it was a very interesting, very unusual activity for a civil engineer. And as I say there, we were talking about a half-ton weight, but everything had to be planned down to the kilo, including the weight of the pilot and all the fuel on board, because we were very close to the upper limit of this particular helicopter in terms of its low capacity. So I'm now just going to play a very short video which actually shows you the helicopter lift being undertaken. So the first phase of this work was to actually land the helicopter adjacent to the structure to attach all the various lifting equipment, which you can see happening here. So during the helicopter lift, there was only 3 people allowed on the structure, and they were all around the navigation bell, which just to attach the lifting shackle, which you can see is happening just there. You can also get to give you an idea of how difficult this area was to access, because it's on the far side of the structure from the walkway. And there you can see the bell has been removed and is now being carried back to shore. And the final challenge was finding a suitable landing site, and there was only really one opportunity, which was on the Widnes side of the river. Again, we had to have an exclusion zone for about 100 meters each side during this operation. So after we removed the structure, it was then refurbished by our subcontractor Tazica, and then it was donated by Network Rail to Holland Borough Council, and they've now put it on display in the Brindley Theatre in Runcorn. The unveiling occurred in October 2018 to coincide with the 150th anniversary of the opening of the bridge. And I said, if you're ever in the area and once we're allowed back indoors again, I'm sure you'll be able to see that if you're interested. It's still on display there, I believe. So the final element of the refurbishment works was the pier fenders. So the original fenders had started to become quite heavily degraded, so the decision was taken to replace the most heavily degraded fenders and replace them with new Eki hardwood. This is quite a difficult material to source. It's being a tropical hardwood, and finding sustainable sources was quite challenging, and we had to ship it halfway across the world from Africa. And we actually had some issues with one of the suppliers, because just getting it onto the ferry, onto the ship, was actually quite troublesome. There was some civil unrest in the area, so we had to find an alternative source. So each of those pieces of hardwood was cut bespoke to each location, and then installed with stainless steel anchors and steel bands to secure it into position. So you can see on that picture there each of the pieces of hardwood, and then you've also got the stainless steel anchors. The banding hasn't been installed in this particular photo. So the actual doing this work, again, quite challenging because of the tidal range of the Mersey. We're talking up to 8 meters at times of tidal range, and you're oscillating between having a dry riverbed and having quite deep water at high tide. So there's a need to control the level of the operational platform. So that's why we had a jack-up rig, which you can see here, this is an 18 by 18 platform with special legs which could be hydraulically lifted and lowered to control the rate of ascent and descent and allow us to work on the fenders. Now, generally, we could only really do the lower halves of the fenders at low tide, but we could still work at the upper ends even when the high tide. However, even on the spring tides, occasionally we couldn't work at all because the whole thing would be submerged. So actually getting to site was actually quite a challenge on this one. So between the airport and Runcorn Bridge, it's about 5 kilometres. It's no longer a maintained navigable channel, although it is open for navigation. And the area is actually, the sands are regularly shifting because of those high tidal flows. So in the end, we had to try and get our rig from Bromber, which is where Carmet are based, and then get it up the estuary up to Runcorn Bridge. And in the end, it took us over a day just to go those 16 kilometres because we had to effectively do it in 2 stages because of the way the tides allow us to move so we won after the first day. We had to essentially anchor the platform in the middle of the river, and unfortunately someone had to stay overnight because we're not allowed, because it has to have a captain at all times. So someone had to, but as I said, throughout the works, actually there was the whole structure had to be, the platform had to be manned to comply with marine regulations. So a bit more detail on those. I said there's full welfare on board, so they are intended to be used as to have people sort of permanently on board them. And we had to operate in 12-hour shifts to suit the tides, and it was manned 24 hours a day for 7 weeks. So this was quite a challenge from a fatigue management point of view. So we did a lot of work with Carmet to try and find a safe way to do this work and try and avoid excessive fatigue. It was obviously very challenging with 12-hour shifts, but we certainly focused on trying to minimise travel distances in particular, so that people were coming off the boat and either putting straight into accommodation or having a dedicated driver to take them home. The main challenge was access. I mean, we could only gain access to the middle of the river at high tide. Again, so that meant we had a narrow window of about an hour every 12 hours to gain access. But there were emergency procedures, but there was only with small inflatables to get off in emergency. So this was our one way in and out, basically. So the Jackal Bridge itself, as I said, the actual rig can only be supplied at high tide as well. So every 12 hours, a boat would come up from Bromborough carrying materials, and then they would leave with any waste materials or scrap that had been removed. And also, while they were there, the boat would manoeuvre the platform into position. So the platform itself doesn't have any power; it has no propulsion. So it's entirely reliant on tugboats to manoeuvre it into new positions, and that can only be done at high tide when we've got enough draft below the boat. It's quite a challenging thing to do because we can only really do it at slack water, because otherwise the flows are too high. So you've literally got a narrow window when the tide turns at the highest point in the tide to actually do that. And it's a very careful process. Effectively, the way it works is one of the legs is left on the seabed, and then the rest are lifted, and basically it pivots around that, and it's effectively walked into its new position carefully to ensure that the thing doesn't drift away down the river. And then once that manoeuvring is done, the tugboat leaves and carries away any waste materials. So one thing I said from a railway, everyone on the project was coming from a railway background, so obviously we're not familiar with working with in the marine environment, so we had to learn a lot of new procedures and skills. So all the crew were actually employed by Carmet because they required special competencies to work at sea. This site was actually classed as at sea, so they had to have effectively the same competencies as someone working on an offshore oil rig. And the only time we as guests were allowed to board it were at high tide, where we'd be escorted and then have to leave before the tide goes out. But the one remaining challenge was the rig itself. It's 18 meters square. There's a pinch point at the north abutment where the pier of the Jubilee Bridge is too close to the existing rail bridge. So there was no room for that 18-meter rig, so we then had to use the workboats themselves. You can see there on the bottom right-hand side, using one of Carmet's workboats rather than the platform to do the work. So that's much slower. It's much more challenging. They haven't got the ability to jack it up, so they're entirely reliant on the water level from the tide. And there's also the water. That area is a lot shallower, so you're absolutely sort of on the banks a lot more. So there's a lot more damage, the risk of damaging the boats. In one case, we actually did damage one of the propellers because it hit a rock, which then had to rescue with the other boat, which is the one you can see on the screen in the image there. So it was a very difficult area to work, and as I said, it's just the nature of them working in a very high flow estuary. So here's again another short video, just to give you an idea of how that work progressed. So you can see here, you've got the south pier where you can see the timbers are lined up, ready to be installed, and they're starting to remove the old ones and replace. And you could probably see the water levels changing constantly and going in and out as well. So yeah, as you see in this video, you can actually see when the barge comes in just briefly as it just nudges the platform around the corner. So that was really a bit of an overview, really, of the refurbishment works we did in 2017 and 18. So I'm going to hand back now to Richard, who's going to take us through the sort of the works we looked at on the bearing replacements.
Oh, right. Okay. Thanks, Mark, and hopefully you can sort of see what a challenging environment it is to work in. I want to try just requesting control from you, Mark, just to make the slides a bit easier. So we'll see if this works. But I did see on the comments there was a question that the walkway trolley wheels were recessed within a wooden guideway, and there is a bit of in answer, yes, they were. We actually relocated some of the supports, some of the beams underneath that walkway to make sure they align with the wheels of the trolley. I don't know if you can add to that, Mark, if that was your area.
Yeah, I mean, yeah, it's a good question, really. I mean, there was a lot of challenges on that eastern walkway. So it's an open mesh. So we couldn't actually run the trolleys directly on the mesh because it wasn't strong enough to carry the weight of those 500 kilo elements. So we actually, we had to reinforce them. We had to strengthen the steel work first, and then that gave us the ability to then carry those weights. And then we used timber bearers effectively with tracks to spread the weight out across the structure a little bit more evenly, and avoid overloading any one of those beams.
Yeah. So if you've got any questions, by all means, put them in the chat, and we'll pick up any at the end as well. Talk about the bearing replacement, which is something that's been in the pipeline for a while, and something that we'd really like to do. It's a fascinating scheme. It's basically the bridge is 3 spans, and it's articulated with 3 simply support spans with roller bearings located over the piers and a fixed point on the south abutment. There's limited longitudinal continuity at deck level through the rail bearers. The sort of the diagram there just shows the rollers. These things are huge, really. They're about 1.5 meters wide and about 3.5 meters long. And what we found when we investigated them is because the deck under itself weight actually deflects, as you'd expect. The front rollers are crushed, and then the rear rollers are actually barely in contact, so they're not really functioning as bearings. And what we've effectively got is 3 spans that are fixed at both ends, which causes its own problems, which we'll go into in a bit. So the cellular box structure over the bearings at each end is to increase the shear strength, and that's the diaphragm walls that I referred to earlier, and that's how that shear strength is located. And basically that's what makes actually jacking outside of those incredibly difficult. So each of the structures is covered by decorative cast iron panels, which you'll have seen in some of the photos. So this is the roller bearings again. You can see from the diagrams there that 11 foot long. These ones at the front are crushed, and then the ones at the rear barely in contact, so they're basically completely seized. So how does that structure articulate? Well, what it does is actually opens up cracks within the piers. So that articulation, there's obviously a lot of locked-in stress into the deck, into the superstructure, but there's also stresses in the substructure which vary seasonally with temperature, and so in the summer those cracks open out close up as the decks expand, and in winter when the structure contracts, it pulls the piers apart. Hang on. Right, there we go. In terms of the bearing replacements, the proposed bearings are rocker bearings. There was a track structure interaction done, and one of the things that was identified through that is that to avoid actually overloading the actual rails, we need to provide some articulation, some rotational movement in the bearings, and that's why those were proposed, and that was really to maximize the structure's life, to provide that articulation that it needs, but also to minimize the stresses in the actual track. So you can see the articulation. You've I say that's existing in a very loose term, because you've got that assumes that articulation as shown there assumes that the roller bearings work, which in actual reality they don't. So it's very much they're all fixed as far as we can tell. And the proposed is to provide a sort of arrangement that will provide for expansion both laterally and transversely. So I talked about the bearing replacement and how difficult that is, and what we've tried to do is look at different ways of doing that. And that's one way is we try and attach our jacking forces to that diaphragm wall, so we're lifting up effectively where the bridge is supported now, and that's probably the safest way to do it. Talked about how we've modelled it with an FE model. One of the really difficult things is we know how it works now, and we've assessed it, and we know that some things are a little bit under strength, but it works. But actually, the moment we start lifting it and actually releasing locked-in stresses and applying loads elsewhere, it's really important to understand how that structure will behave then. So this is one of the solutions that we came up with, which is quite intrusive. It will require quite a lot of intrusive works to remove stone and to make pockets in it in what is a listed structure. So that would be quite challenging to agree. So yeah, replace the existing bearings with modern bearings, the lattice structure. So we're looking to jack that where the existing diaphragm wall is. But an alternative could be to use a temporary steel work to actually extend that diaphragm wall outside of the piers. So we've done a lot of ECI, and we've involved Arcadis, the designer, who've done the FE modelling. We've also had advice and peer reviews from Cass Haywood. Substantial temporary works are likely to be required, and we're going to have to mine out those existing bearings that they're seized. It's not going to be something we can just pull out quite easily. This was some work that we did with Fresnay, which is they support us with a bit of ECI, and they've looked at actually the practicalities of doing it. And as you can see, where that free space is on that left, that's all granite and sandstone now. So it would be an extremely intrusive way of doing it. But the idea there is really to try and do as much of this work as we can while trains are running, so that we're not actually affecting the West Coast Main Line. Another option was to try and jack it from above with strand jacking. Again, less disruptive. There's less sort of that mining operation there, but you've still got to get your jacks there. You've still got to get that in and lift that structure and release those locked-in stresses and try and model what happens. So the two, this is one of the options I referred to, where we put these artificial jacking shelves in place and we try and jack it outside. Now that's feasible, but would require some substantial strengthening of that lattice work. Progressive bearing replacement mining. This is I think this is actually possibly one of the easier ones, but most intrusive to the structure. I say easy in a very loose sense. There's no easy options here. So it's probably going to require the bridge to be temporarily lifted to allow access to the bearings. Its strategic location on the West Coast mainland limits opportunities for long blockade. I suppose if we were doing this in 20 years' time and you've got Northern Powerhouse Rail and HS2 in place, this bridge becomes less of a strategic route. But given that it's the only way over the river, it's always going to be strategic for commuter and regional traffic. So I think, it just needs careful planning, but it is going to be a long blockade. Long viaducts and the long viaducts on each side of the bridge really limit options for a temporary track alignment, and the safety of trains while the bridge is in a jack position to be considered. Ideally, we would jack it up just nominally to free the bearings and give us some working room, and actually try and get the track in a position that it can still be used with a speed restriction. But given the seized bearings, the locked-in stresses, and the difficulty in determining the behaviour of the bridge, it's very difficult to predict, even with a three-dimensional finite element model. So, in summary, Runcorn Bridge is likely to remain an important strategic asset for the foreseeable future. Phase 2 works have secured the immediate future of the structure. And it's extremely challenging, and we know it's an extremely challenging site due to the constrained site with the multiple interfaces and that marine interface and the tidal flows through there. The like-for-like replacement of the cast iron parapets was a complex activity, and the bearing replacement, it's a high cost and high risk activity. There is a case for adopting an enhanced maintenance regime to manage the seized bearings. I suppose what we mean by that is that when we did the sort of ECI, and we had a lot of discussions, effectively the bridge as it stands, it articulates, but it does that in a way that was never intended. It does that through effectively using the cracks in the piers and the seasonal and thermal movement. Now, is that a sustainable case? I've heard the opinions both ways, that actually why take the risk of disturbing this structure with its locked-in stresses and when you're not entirely sure what's going to happen, or do you actually just maintain what's there and accept the fact that there are these cracks in the piers and the abutments that will fluctuate, the movement will fluctuate through the seasons? It's a good debating point, and I'm not sure there's a right answer. When we looked at the cost for replacing the bearings are probably north of 15 million. But then when you look at this structure, if you were to replace it, you're looking at hundreds of millions. So it's an interesting question, one we debated quite a lot the last time we looked at this. And that really concludes the presentation, but quite happy to take any questions if anybody's got any.
Hello, Richard. It's John here.
Hi, John.
I think you've answered the next question, haven't you, about the walkway trolleys?
That's right. Yeah.
Yeah. It was interesting. The walkway use of that was interesting. The outriggers don't look. You look fairly flimsy. Did you? Were they quite near the limit when you had all that heavy cast iron running over the top of them?
I'll say that one, Richard. I mean, yeah. So obviously, the outriggers are intended to have the cast iron. Actually, they do actually support the parapets themselves. They are very far on the tips, so they can accommodate it. Which is obviously in the temporary case, we were doing some quite substantial modifications to them to try and repair and strengthen them. So we did have to be very careful as to not to overload them in that state. But no, I think they're a lot more substantial than they actually look. They're actually quite thick raw time plates, and actually in surprisingly good condition, really, considering they've been there for 150 years.
I think it's fair to say that there was a lot of temporary works assessment done for the structure, to not just to design additional supports, but to assess what was there and make sure that what we were doing to it wasn't going to overstress it. And it's kind of a micro version of what we'd do if we were ever going to replace the bearings.
Right. Okay. Well, whereabouts did you get the ironwork cast? I know we did the approach viaduct a good few years ago, and a firm near Newcastle did that work.
Mark, do you want to take that?
I'll take that one. Yeah. So obviously, we actually did try and find the firm that did it originally, but unfortunately they went out of business before we got to our project. So we used a company in Preston, Shakespeare Foundry.
Oh, right.
And also another one in the Black Country as well. I can't remember the name off the top of my head, but we ended up using two foundries in the end to try and sort of speed things along as best we could.
Well, that's interesting. I live in Preston, and I'm not aware of that, so that's interesting. Thank you. Do we have any other questions from anybody, either on the chat or using the microphones?
It's Phil here, John. I'd just like to ask. I see that the bridge is actually listed Grade 2 star rather than Grade 2, and I wondered what features of the bridge made it worthy of that extra special listing.
Yeah, it's a good question. I think it's a combination of it's at the time it was one of the longest bridges in the world when it was built, and I think it's also it's very ornate. As you can see on screen now, there's the stone parapets at each end. I think also William Baker. I think this is like he's got one of his crowning achievements as the engineer for the railway at the time. So I think there's all the combination of those factors as why it's got that Grade 2 star listing.
Thank you. Thanks.
Yeah, you can see actually working on the structure that they've actually spared no expense in making it quite grand, from that sort of castellated abutments to the cast iron sort of shrouds around the diaphragms. There's a lot of care and gone into the construction of this, and that's something that it would be very difficult to sort of not disturb with any more intrusive works, but it's a really impressive structure when you get close up to it.
Yeah, well, thank you.
I guess it's unique in a lot of ways as well, isn't it?
It is. When you compare it to the Silver Jubilee, it complements it very well. If you look from the seaward side, it sort of frames it, but it's quite unobtrusive compared to the Silver Jubilee. But up close, it really is impressive. But we wouldn't, myself and Mark have been, we've been fortunate enough to actually be on that structure and get up onto the turrets and see what it's like.
Yeah, I think, as you say, the piers are hollow, I think, aren't they? I think there was access to the piers at one time from in the 6 foot. I'm not sure whether that still exists or not. Yeah,
I think it's the abutments are voided, and Mark, correct me if I'm wrong, but I believe we sent in, those were inspected by a sort of confined space team. We proved that the piers that are a bit more slender are solid, but yeah, the abutments certainly have sort of vaulted voids inside.
Right.
Yeah, no, that's right, Richard. Yeah, the abutments are hollow, but the piers themselves are largely solid. There are some voids in the piers as well, but towards the bottom, but yeah, largely solid. You can get, yeah, in theory, you could still gain access. The actual accesses are still there, but they've been covered over. But you'd have to be very, very, very thin and very small to get through some of those holes. They are tiny.
Likewise, the top and bottom booms. Did you do an internal inspection on those remotely? Or at one time they used to put men into them, but you wouldn't do that today, I don't think.
The box sections underneath the main girders. I don't think we looked at those, did we?
No, there's no access directly. So there's access to the diaphragms at each end, which are like box structures. There's like there were some ladders inside there, but they'd completely corroded away, so we actually removed them because we decided there was no longer a safe access there. The box beams themselves are too small for someone gets one inside, but there are inspection holes all the way along the sides, which we discovered actually when Network Rail weren't aware of them when we were on site until we actually pointed them out. They've been filled with sort of rubber wooden bungs and then painted over, so they didn't realise they were there. It was only when we grip blasted the structure that we actually discovered them. So we've replaced them with removable rubber bungs, so to allow them to be used for inspection in the future.
I'm sure you could crawl through them, but I don't think you'd get much else space in there. Which makes it does make you wonder how we managed to verify the assessment, but I'm sure they must have done something. We used an endoscope to try and see what was going on with the bearings and actually get some pictures. And that's how we know that the front rollers are crushed.
Yeah, I mean, it's probably worth noting the structure is actually in remarkably good condition for its age. It's held up very well. There's just most of the only real sort of issues we identified were sort of surface corrosion, which could be relatively easily treated with a bit of a grip blast and paint. So the intention will be is if this structure, when the bearings are dealt with, there will be a more substantial maintenance intervention, including a full repaint, I think, of all the ironwork.
I think it's been such a major structure. It's been well looked after, hasn't it, over the years?
Yeah, it's just little things. The box girders, the troughing that sit at the bottom, they sort of collect water, and you don't really want to put penetration to the boxes because that would just lead to internal corrosion. So they've got these spitter pipes. When it gets to a certain level, it gets rid of it. And we had a lot of discussion. Well, how do we improve the drainage? And in the end, we just said, well, why don't we'll just spray it with eliminator, so that effectively it's fully waterproof, and accept that it would hold that water. And that was the best solution that we could come up with. And it's effectively what it does already anyway.
Oh, good. I don't know if we have any more questions. I can't see any on the chat. If anyone wants to ask any with the microphone, they can do. But if there are no more, I'd just like to thank both Richard and Mark for giving us such a fascinating insight into the work. It seems to have been a really thorough sort of restoration, what's been done so far. And I know most Liverpudlians who've travelled south over the structure would be grateful for that. And as you say, it's a major structure on a major route. So we look forward to perhaps the bearing work in the future. But I take your point. It must be. There's a certain amount of risk there in that we don't know how the locked-in stresses are going to affect any works that are done, and maybe there is an argument for just monitoring it in its current state. So that'll be a big decision for somebody. So maybe we look forward to hearing about that in the future. So thank you both, and I'd ask people to perhaps unmute their microphones and thank you in the normal way. But thank you anyway.
Thanks.